It's the summer of 2019. You, a lazy functional programmer, decide to spend your time indoors and you're blissfully unaware of what 2020 has in store for you. So you're inside and it starts to get pretty warm. You check the temperature and it's about 32 degrees Celsius. That's pretty hot. Maybe you should open the window. But then if you open the window, you have to close it back when you leave the house, or for example, when the temperature becomes too low. So this act of mechanical effort is not very appealing. So on your behalf, you decide that you're going to set up an IoT system which is going to control the window for you. So you buy a little microcontroller which can run on a tiny little battery, and you decide to call the application that you're going to run on this board Alexa. So here are the use cases that you can think of for Alexa. If Alexa can determine that you are indoors and if the temperature is greater than 30 degrees, it must relay a signal to the window asking it to be open. This can be done, for example, by sensing the data from the sensors in the house and by relaying a signal to the controller or the motor which controls the window, right? So if the temperature is lesser than or equal to 30 degrees, Alexa must essentially ask for the window to be closed, right? But if you're outside, regardless of the temperature, Alexa must ask for the window to be closed. Okay, good enough. So it's a very simple application. But before you can actually implement this application, you're already faced with a number of challenges. So for example, the inputs are already a challenge because they're changing over time, right? So for example, the temperature constantly varies over time. And also these changes in inputs need not be periodic in that they need not happen over fixed intervals of time, and they need not be synchronized with other inputs, right? So for example, over here, the temperature changes from 30 degrees to 31, but there's no change in the status of the user in terms of being indoors, right? So you need to identify a solution to these problems before you can actually write this program down. But the most important problem of all is that the software development kit offered by the board is very low level in that it uses C. This means that you have to manually manage your memory, possibly using pointer arithmetic. It becomes difficult to protect sensitive data in your system. For example, you may want to make sure that your whereabouts are not leaked to an intruder. And last but not the least, you really do not want to handle segmentation fault error messages because they're just horrible and they're giving you the sweats. So you don't want to program in C, but the board's SDK supports only C. So what are you going to do? And this is the question that you're faced with. How should you program Alexa? So I'm here, me, the guy with the longest name, along with other co-authors on the paper, to tell you about how we think Alexa and other similar reactive IoT apps should be programmed in Haskell using an eDSL, right? This also happens to be the goal of our project. So the main idea that I'm here to tell you is that we think you should program Alexa and similar reactive IoT apps using a Haskell eDSL, which then generate C for you so that you don't have to write C. And you enjoy writing Haskell, so why not? So to show you what I mean by reactive, what I would like to do is essentially simulate the situation of Alexa. And what we're going to do is I'm going to use my phone and I'm going to relay sensor information, that is the temperature and the status of the user, via Bluetooth to the microcontroller. And then the application running on the microcontroller is then going to use these inputs to identify whether the window must be opened or closed, right? And of course, the whole point of this demo is that the app running on this board is written using the eDSL that we're proposing. So let's go ahead and jump to the demo. So what you can see here on the left-hand side is my phone. And on the right-hand side, you're looking at the terminal of the application. I mean, the standard output of the application. And so in the bottom left of the phone, you can see there's something called sensor location, there's something called temperature. So let's start off by assuming that the user is indeed indoors, and this is the way I've set it up already. So now let me go ahead and try to change the temperature to something like, say, 28 degrees. That's not too hot, well, at least in the south of India. So when you do this, Alexa relays a message saying, hey, window, close, because, well, it's not too hot or it's a bit cold, right? So, well, the window closes. And on the other hand, if you set the temperature to 35 degrees, which is sort of simulating an update in the temperature signaled by a sensor, So then Alexa immediately says, oh, well, the temperature's increased, it's too hot, please open the window, right? So we've changed the temperature sensor so far. Let's go ahead and change the location of the user to have been having left the house, left the premises, right? So I'm gonna write 0 for that to indicate that the user has left the house. And then suddenly Alexa says, well, okay, if the user has left the house, you must absolutely close the window immediately, right? So this is really what I mean by reactive IoT apps, right? So they're reacting to a change in the input. Okay, great. So so the app which we just saw was written using Haski, an eDSL that we're going to be talking about today. And Haski is essentially a monadic eDSL. And in Haski, you program these reactive apps as Haskell functions, which accept inputs as streams and produce an output also as a stream. And when compiled, a Haski program generates a C program, which contains a C function, which corresponds to the Haski program that you originally wrote. And this C function is called a step function. So for a Haski program, let's say prog, it generates a prog step function. This function also receives similar inputs and produces a similar output to that as your original function, but also has some additional bookkeeping to maintain the memory of the program, right? And the way, since this is going to come up again, the way to think about this step function is that this produces a value of the stream when invoked. So continuously invoking this function continuously produces values of the stream. And this is how we're going to view this function. Okay, so let's get back to Alexa. How should we program Alexa in Haski, right? So Alexa is essentially going to be a simple function which accepts two stream inputs, one indicating the status of the user and the other indicating the temperature, hence a stream integer. So status is essentially an optional action or a maybe action, which can be in or out. And the output stream is essentially that of a window operation, which can be either open or close. So these are the types that we're going to set up for our program. So now let's actually go ahead and write down the function. Okay, so it's just 7 or 8 lines, so like bear with me. Okay, so first we start out by declaring to the compiler saying, hey, I'm going to write a piece of code that you must in turn generate C for. And we do this using the node combinator. We provide a name for this program, and we go ahead and continue writing the rest of the functions as we would do in regular Haskell. So we start out by defining a stream. A Haski computation is essentially just a sequence of streams. So first we define a stream called isHot. And the purpose of this stream is to denote whether it's a Boolean stream, which denotes whether the temperature is crossed at a given threshold. So it reads as isHot is a stream, which is defined to be a Boolean stream, which is true if the temperature is greater than 30, and false otherwise, right? So we need another stream called recent act, which essentially gives us the most recent action of the user. And for this, we must look into stat. Now remember that the status update of the user might be nothing, right? So if it is nothing, we must use the last available update of the user. And this is exactly what we're doing in this line here. So we match on stat using the combinator match. And then if it happens to be nothing, that is there's no update, just use the past action. If there happens to be an update, then use the current value using the val combinator, which simply injects a value into a stream. And past act is defined as a stream which simply starts out by being out and then is followed by the next available recent action. So you can think of this FBY followed by combinator as a cons operator, but for streams. Okay, so finally, now that you have both the pieces, that is isHot and a recent act, now you're ready to compute a decision of whether the window must be open or closed. So we do this by, once again, matching on recent act. And what we're going to do is we're going to inspect the value of recent act. If it happens to be in, then depending on the temperature, we ask for the window to be open or closed. If it's out, then we just ask for the window to be closed. And that's it. And then you return the final decision. This is the entire program that we're after. And this captures the core logic of the application that we're interested in. So now what I want to do is walk through that very piece of code, but like look at small pieces of it with you. And we're going to look at an overview of what makes those things come together and work to generate C. So one of the things we're looking at is a mutually recursive definition. So recent act and past act were defined mutually in the sense that they used each other to define themselves. And this is made possible by the mdo keyword, which is available by the recursive do language extension. But of course, you can define mutually recursive streams because Haski has an instance of a monad fix of the monad fix type class, right? So I don't want to go into the definition of what exactly mfix is, definition of mfix, but here I really want to give a shout out to recursive do and say, look, recursive do is what allows us to do this kind of programming, that is mutually recursive streams, any number of them. Okay. And the other interesting thing in the piece of code that we saw earlier is pattern matching, right? So because if you recollect, we actually pattern matched on recent, and by pattern match I mean use pattern matching in Haskell, because this is the case keyword in Haskell, and we use and we would write the rest of the cases and the branches just like we would in Haskell. And the interesting thing about this piece of code is it actually generates a pattern matching in C. Well, of course, you don't have full-blown pattern matching. You generate a switch case statement in C, which gives you the necessary branching, which switches over recent act, and in each case actually assigns the corresponding value to the variable dec, which is the decision that we're trying to compute. As a reminder, \case is just a way of saying lambda x case x of. So this is really just regular Haskell pattern matching that we're using to pattern match in the target. So, but how is this made possible, really? So for that we need to look at the type of match. And match has a type which accepts two arguments. One is a string, which we're pattern matching over, and the other is a function, which essentially transforms values of the stream into different streams, right? And so now what we can do is, in the process of defining a function, we can just pattern match over the argument, and that's exactly what we're doing here. But the real secret is in being able to transform this function into a pattern matching statement or a switch case statement in C is really this constraint which requires the scrutinized or the pattern matched over stream to be finitely enumerable. The reason this enables code generation is because now what you can simply do is enumerate all possible values of A, take this function, apply it to all the values, and then now you can extract all the branches of the case, and then further sort of generate code for each branch. So this nifty little trick is also called the trick in partial evaluation. And the other thing, the final thing which I want to mention about that example is that the node combinator. The node combinator is actually quite interesting because what it does is it takes a Haskell function and transforms it to a C function. So over here it's taking this function, that which defines Alexa, and it generates a HAL step function similar to the step function I showed you earlier, which once again receives similar arguments and produces similar output and some bookkeeping arguments which are used internally. In this case, the bookkeeping argument is used to which is used to retain some memory, which is exactly the previous act that we had defined earlier, right? Because the only piece of memory that we need is to keep track of the last successful update in the action of the user. Okay, so so like I said, the magic is really behind the node combinator, which has a type which allows it to be given a name and a function, and it returns a function of the same type. I mean, of course, at the surface, this is not so obvious why or how this works. And this is all hidden behind the constraints which constrain types A and B. So I don't want to go into this, but the intuition here is that we return a function in place of the original function for which we know how to generate code. And we are able to do this, of course we cannot do this in general, but we are able to do this because we restrict A and B to certain functions which allow exactly functions of these kind, namely functions which accept streams as inputs and produces stream as an output inside the Haski monad. It's exactly these kind of functions that we're after. You can look at the details in the paper. So the other, the key functionality of Haski is that it supports a lightweight information flow control extension. And what information flow control allows you to do is talk about the flow of sensitive information within your system. So you can do this by using labeled streams, right? So labeled streams is essentially just streams tagged with the sensitivity label. And we talk about label streams using the LStream type here. And label streams can be programmed against using labeling primitives. So here are two such primitives. One is label and unlabel. A label associates a label with a stream and produces a label stream. So here what we're doing is we're saying that use the high label, which is a label which indicates that the information is of high sensitivity, and we give it the status stream, and then it produces a label stream which is of high sensitivity. Now you can also unlabel label streams and produce a regular stream. There's no other requirement here, but of course the unlabeled performs a side effect which requires the unlabeling program to be run in a higher security context. So it demands more on an invocation or an execution of the program which unlabels. And there are more such primitives, but you can look at them in the paper. So how does this really change how Alexa is written, right? So if we change the type signature of Alexa, as I showed you earlier, so then what happens is that now a programmer trying to write a secure version of Alexa is forced to unlabel the secret status stream and also label the resulting decision stream. So like I said, unlabel raises the requirements of the computation, and label essentially labels it back. And the interesting thing here is if the programmer, for example, tries to label the decision public one while the status of the user is a secret one, the Haski compiler is going to complain, hey, you're not doing something right, that's not okay, and compilation is going to fail. So the interesting thing here is that this is compile time information flow control, but it's not done using types. What that means is the label high is a value of the type label, and high is not a type in itself. This is a little bit different from how static information flow control works, because typically this is done, the enforcement is done by using the Haskell's type checker. So instead, we're going to do it during compile time, but it's just done by the Haski compiler as opposed to being done by the Haskell's type checker. And we do this by essentially computing away the IFC primitives. And what this means is that a secure Alexa program and the Alexa program, they generate the same code provided there's no violation in any security policies which have been set. Okay, so here's the overview of what we're really looking at here. So Haski is an embedded domain-specific language. It does not require any sort of custom modifications of Haskell compiler to be performed. So what happens, what you're doing when you're compiling a Haski program is you're just calling a Haskell function, and it essentially what it does is it builds a sequence of string definitions, and these string definitions are in turn transformed into a sequence of Lustre nodes. And these Lustre nodes are essentially sub-programs of a larger program in Lustre, and Lustre is a synchronous data flow language, which is popular for programming embedded systems. And so the compilation of Lustre is fairly well understood, and we don't go into this in the paper. Instead, we focus more on the embedding techniques that enable Haski, and also the information flow control enforcement which happens during embedding, which I think is quite interesting. So to kind of get back to Alexa once again, and I'd like to tell you about what exactly was going on when I run Alexa using my phone and this little board which was sitting here all along. So what we were doing was we compiled Alexa, which generated a bit of C code, and then we took the C code, tied it up with a little bit of runtime for the operating system, which is Zephyr, and then we finally run it on the board. So Zephyr is a real-time operating system with a callback-based C API, and we use this because this provides a slightly more standardized interface than the SDKs of boards themselves. So now, for example, we may as well be using a different board, and it wouldn't really change how the application works. Okay, so the linking of the code generated by Haski with the Zephyr API currently requires manual intervention. And what I mean by that is the HAL step function generated by the Haski compiler needs to be registered as a callback to when the inputs for the function are available. So for example, when the notification of a temperature a change is triggered, then this must call the helstep function with the new temperature and saying, well, there's no change in the status of the user, and by giving it the memory of the program. So this little sort of linking and tying up the generated code with Zephyr's API is currently done manually. But there's no reason why it shouldn't be possible to generate this also. So by this time you're probably going, oh, yet another eDSL. Well, okay, so let me at least give you a little bit of perspective of where we are in this sort of entire spectrum of domain-specific languages and also general-purpose programming languages. So on the left-hand side, we have these code-generating eDSLs such as Ivory, Copilot, and Haskell, which are really focused on generating C and lifting lower-level abstractions to a higher-level language and programming them in a type-safe way. And in the middle, we have synchronous data flow application languages, which are really focused on embedded systems, and they're essentially Lustre and the family of languages such as Cascade and Lucid Synchron. And also, we have functional reactive programming, which many of you might be aware of, right? So Haski is essentially somewhere in between code-generating eDSLs and synchronous data flow applications. And Haski tries to, it's very much based on the Lustre paradigm, and it tries to generate code which can be run with a fixed amount of memory, right? So that you can put a bound on the amount of memory that is consumed by the program, which is very important for these resource-constrained IoT devices. So, in a nutshell, to conclude, here's what I'm trying to tell you, right? Haski is a Haskell eDSL that you can use to program resource-constrained IoT devices, specifically reactive IoT applications, while actually doing static information flow control to secure the flow of information within your system. And that concludes my talk. Thank you.